What if the softest sound you'll ever hear isn't carried by wind or voice, but by time itself? Imagine for a moment a whisper that does not begin in the present, a signal that travels backward, brushing against your consciousness before the event it foretells has even occurred. It is a thought both thrilling and disquieting, a shiver in the spine of reason. And yet from ancient prophets to modern dreamers, humans have long claimed to glimpse tomorrow before it arrives. Consider the strange case of Morgan Robertson, a relatively obscure novelist of the late 19th century. In 1898, he published Futility, a tale of a grand ocean liner described as unsinkable, striking an iceberg in the North Atlantic and vanishing beneath the waves with horrifying speed. 14 years later, the Titanic, bearing uncanny similarities in size, design, and tragic fate, met precisely that doom. Critics of the time grasped for explanations: coincidence, subconscious pattern recognition, the mere inevitability of human engineering hubris. But others wondered whether Robertson had tapped into something far more unsettling, an echo from a future he could not consciously know. It is easy to dismiss such stories as the accidents of history, the random overlaps that confirmation bias loves to collect. After all, for every supposed premonition that finds a stage, countless forgotten hunches wither unfulfilled. Skepticism is a habit as old as curiosity itself. Our rational minds demand evidence, control, replication. And yet, the magnetic pull of prophecy persists. From Delphi's oracles cloaked in vapors of mystery to the dream journals of modern-day visionaries, we return to these tales with a hunger that science alone has never fully quieted. Something in us craves the idea that time might be more porous than the ticking of our clocks admits. But how could such a thing be possible? For centuries, physics has stood as a fortress of cause and effect. Past begets present, present begets future. Time, in the classical view, flows like an unyielding river carrying events downstream. Yet the 20th century cracked that certainty. Einstein's theory of relativity revealed time as flexible, entangled with space itself, stretching and warping under the influence of speed and gravity. The notion of a single universal now dissolved. What is present for you may be future for another. Already the clean hierarchy of past and future was not as simple as it seemed. Relativity, however, merely bends time. It does not reverse its current. For that, we turn to the stranger domains of quantum mechanics. In the subatomic world, particles behave in ways that mock our common sense. A photon can act like a wave and a particle simultaneously. An electron's path is a cloud of probabilities until we measure it, at which point it chooses. In these microscopic theaters, cause and effect sometimes appear to blur. Physicists have designed delayed choice experiments, quantum erasers, where decisions made in the present seem to determine the behavior of particles in the past. Do these experiments truly imply retrocausality? Or are we simply misreading the mathematics of probability and measurement? Debate rages. Some interpretations suggest that information can indeed travel backward, that the act of observation can reach into history's ledger and rewrite the outcome. Others argue these results merely expose our incomplete language for describing a world that does not share our intuitive sense of time's arrow. Meanwhile, cosmologists confront the puzzle of entropy, the one-way growth of disorder that gives time its apparent direction. The early universe was improbably ordered, and as it evolves, entropy increases. This is why eggs break, but do not unbreak, why memories form of the past, but not the future. Yet the laws of physics themselves at the deepest level are remarkably indifferent to time's direction. Whether we run the equations forward or backward, the mathematics holds. Why then does our experience march relentlessly forward? Could the asymmetry of entropy be more a feature of perception than a fundamental law? This tension between theory and experience invites speculation. Perhaps, some whisper, the future is already laid out as a static block in which past, present, and future coexist? If so, what we call now is merely our consciousness sliding along a dimension already complete. In such a universe, might information from a later page occasionally bleed into our current one, like ink seeping through thin paper? Such notions teeter at the edge of science and philosophy. To the experimental physicist, extraordinary claims require extraordinary proof. To the philosopher, the very question of time's reality remains unsettled. Is time an objective feature of the cosmos, or a construct of the mind-organizing change? When we dream of tomorrow, are we glimpsing something real or simply weaving patterns in the chaos of possibility? And yet, even the most hard-nosed skeptic must admit, history is thick with the unsettling sense of foresight. Premonitory dreams of disasters later confirmed. Artists and writers sketching uncanny parallels to events decades away. Scientists themselves confess to insights arriving as if from nowhere. Sudden illuminations whose timing defies explanation. Coincidence, perhaps. But coincidences have a curious way of gathering into constellations. The human psyche, after all, is wired for pattern recognition. We survive by anticipating the future, by spotting the subtle clues that signal danger or opportunity. Our imagination of tomorrow is both an evolutionary tool and a source of wonder. It blurs the line between rational forecast and something that feels far stranger. When we listen for whispers from the future, are we merely hearing the echoes of our own predictive minds or something more? Physics offers both solace and provocation. It tells us that time is not what we thought, that simultaneity is relative, that quantum reality may permit correlations across time. Yet it stops short of confirming prophecy. The universe, like a master storyteller, keeps its deepest plot twists just beyond our grasp. Still, the question lingers if the future is already written. Even in the silent language of possibility, might it sometimes be written back? Perhaps the very doubt that drives science and the awe that fuels myth are two faces of the same mystery. We stand, as we have always stood, between skepticism and wonder, straining to hear a sound that might be nothing or might be tomorrow itself. Calling us home, time seems to move with the quiet authority of a river, steady, unstoppable, and absolute. We wake, we age, we remember yesterday, but never tomorrow, and we trust the tick of the clock as though it was stitched into the fabric of reality itself. Yet beneath this comforting rhythm lies a question that unsettles the very core of our understanding. Why does time have a direction at all? Physics, at first glance, offers a simple guide. The thermodynamic arrow of time tells us that entropy disorder tends to increase. A cup of hot coffee cools. Shattered glass never leaps back into wholeness. The second law of thermodynamics describes this relentless drift toward equilibrium, and it is here that we locate the sense of before and after. From melting ice to the dying stars in distant galaxies, every process whispers the same truth. The universe slides toward greater chaos. But pause for a moment. If entropy is the grand conductor of time's symphony, why do the fundamental equations, the mathematical heartbeats of classical and quantum mechanics, refuse to choose a direction? Newton's laws, Maxwell's equations, even the Schrödinger equation all work just as elegantly if you reverse time's sign. Imagine a film of planets circling a star. Play it backward, the orbits remain perfect, the equations hold. On this deepest level, nature is ambidextrous with respect to time. This contrast between the irreversible macroscopic world and the reversible microscopic one creates a tension that has haunted philosophers and physicists for centuries. Ludwig Boltzmann, in the 19th century, sought to reconcile it by linking entropy's growth to the statistical behavior of countless particles. The universe, he argued, simply started in an extraordinarily low entropy state, and the climb toward disorder is the most probable path forward. Yet probability is not a necessity. The laws themselves still allow the cosmic movie to run backward without contradiction. Consider a thought experiment. Picture an isolated box filled with perfectly elastic billiard balls. Let them bounce and collide for hours. The pattern of their motions, governed by Newtonian mechanics, could be reversed, every ball retracing its path with mathematical precision if we were to reverse all their velocities at a single instant. Nothing in the equations forbids it. Yet in practice, the tiniest disturbance, a grain of dust, a breath of air, erases this symmetry. The directionality of time emerges not from the laws, but from the fragility of conditions. Quantum mechanics complicates the story further. In the quantum realm, time enters the Schrödinger equation as a parameter, not an arrow. The wave function evolves smoothly whether we move forward or backward. But measurement, when a quantum system collapses into a definite state, seems to introduce an asymmetry. Before measurement, an electron can occupy a haze of possibilities. Afterward, it stands committed to a single outcome. Some interpret this as a quantum arrow of time, born from observation itself. Others argue collapse is only apparent, that decoherence and environment produce the illusion of irreversibility. We are left with a haunting paradox. The universe's most fundamental rules are time-symmetric, yet our everyday reality is drenched in one-way experience. The arrow we trust is not etched into the equations but drawn by initial conditions and the improbable low-entropy dawn of the cosmos. Like a grand stage set, time's direction may be less a law and more a fragile consequence of the universe's opening act, quantum entanglement. Even the phrase hums with something otherworldly, as if it were describing the hidden machinery of a cosmic puppet show. At first glance, it sounds like poetic mysticism. Two particles, born together and then flung to opposite corners of the universe, yet behaving as if some invisible thread binds them in perfect synchrony. But this is no metaphor whispered by dreamers. It is a real, measurable fact of nature, one of the most astonishing revelations of modern physics. Picture two electrons sharing a moment of creation. Their quantum properties intertwined like twin dancers in a single performance. Separate them by a laboratory table, a continent, or the vastness of interstellar space. Measure the spin of one, and the other will instantly reveal a complementary orientation. No signal travels between them, at least not in any way that fits the limits of light or the logic of classical causality. The universe, it seems, holds a kind of secret wiring that defies our ordinary intuitions of distance and time. The idea first startled even the architects of quantum theory. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen posed a provocative challenge now known as the EPR paradox. They suspected something incomplete in quantum mechanics. If two particles could remain correlated at a distance, then either information must travel faster than light, violating Einstein's own theory of relativity, or the quantum description lacked some hidden variables that would restore an orderly, local reality. Einstein famously dismissed the strange correlations as spooky action at a distance, confident that a deeper, more sensible explanation would one day emerge. For decades, the debate simmered. Niels Bohr defended the standard quantum view. The wave function, with all its ghostly probabilities, is not a mere statistical shortcut, but a full description of reality. Einstein countered that nature must conceal underlying variables that determine outcomes, even if we cannot yet see them. The argument crystallized into a deeper question. Is the universe fundamentally local, with influences limited by the speed of light? Or is there an irreducible non-locality stitched into the fabric of existence itself? It took a brilliant twist of mathematical insight to move the discussion beyond philosophy and into experiment. In 1964, the Irish physicist John Bell devised a theorem that would forever change the conversation. Bell showed that if hidden, variables existed and obeyed the principle of locality, faster-than-light communicationness, then certain statistical correlations between entangled particles would be bounded by precise numerical limits. Quantum mechanics, by contrast, predicted that entangled particles could break those limits. Bell's inequality became the litmus test. Violated, and the comforting dream of a purely local reality collapses. The challenge was formidable. To test Bell's inequality, one had to produce pairs of entangled particles, measure their properties with exquisite precision, and rule out every loophole that might let ordinary physics masquerade as something extraordinary. Early experiments in the 1970s hinted at violations, but skeptics pointed to potential flaws. Detectors were inefficient. Random choices of measurement settings might be subtly correlated. Signals could, in principle, sneak through unnoticed. Yet the evidence kept mounting, and the stage was set for a definitive trial. Enter Alain Aspect and his team in the early 1980s. Working in Orsay, France, Aspect crafted a series of experiments that became landmarks of 20th century science. By rapidly switching the orientations of polarizers while entangled photons were already in flight, he closed key loopholes that might allow hidden variables to fake the predicted correlations. The results were striking. Time and again, the measured correlations defied Bell's classical bounds and matched the predictions of quantum mechanics. Nature has spoken. The universe is not constrained by local hidden variables. The spooky action Einstein mocked was no longer a curious metaphor. It was an experimental fact. But what does this mean? Does some ghostly signal leap across space faster than light, carrying information instantaneously? Relativity forbids any signal that could be used for faster-than-light communication, and indeed, entanglement stubbornly resists being exploited for such purposes. No matter how perfectly synchronized the outcomes, one cannot control them to transmit a message. The statistics reveal their pattern only when measurements from both sides are compared later, through ordinary sublight channels. The universe preserves its cosmic speed limit even as it flaunts our classical intuitions. Still, the implications are profound. Entanglement forces us to abandon a picture of particles as independent, self-contained entities. Instead, reality at its most fundamental level appears holistic. The properties of each particle are not pre-written like the numbers on a hidden card. They are defined only in relation to the other, as though the pair constitutes a single system stretched across space. The universe, in this sense, behaves less like a machine of separable parts and more like an undivided web of relationships. Philosophers of physics have wrestled with this revelation for decades. Some argue that entanglement merely reflects the peculiar bookkeeping of quantum mathematics, a convenient but ultimately abstract formalism. Others see in it a profound clue that reality is not local, not even in principle that space itself might be less fundamental than the correlations that dance upon it. Is entanglement the signature of some deeper layer of the cosmos, a hidden architecture where information travels in ways we have yet to fathom? Or is it simply that our classical notion of travel is obsolete, that the quantum world is not a place of objects moving and signaling, but of patterns of potentiality that become actual only when observed? Consider the strange tension. On one hand, the experiments are among the most rigorously verified in all of science. Modern loophole-free tests using fast detectors and even cosmic photons to choose measurement settings have repeatedly confirmed the violation of Bell's inequalities. These are not fragile anomalies. They are as real and repeatable as the orbit of the Moon. On the other hand, the phenomenon they reveal seems to whisper of something beyond the familiar scaffolding of cause and effect. We are forced to entertain the possibility that cause and effect, as we usually conceive them, are not the ultimate grammar of nature. The philosophical stakes reach further still. If entanglement transcends space, might it also defy time? Quantum correlations have been demonstrated between particles whose measurements are separated not only by kilometers, but by intervals where one measurement is decided after the other's outcome is already fixed. Experiments probing delayed choice scenarios suggest that the decision of what to measure can seemingly reach backward, defining the history of a particle in ways that appear retroactive. It is not that signals travel back in time, no. Paradoxical messages emerge, but that the very distinction between past and future wavers when examined at quantum scales Some physicists speculate that entanglement is the glue holding the universe together at the most fundamental level. Theorists exploring the union of quantum mechanics and gravity, particularly in the strange geometry of black holes and the fabric of space-time, have proposed that space-time itself might be a manifestation of quantum entanglement. According to the EPR conjecture, named for Einstein-Rosen and Einstein-Podolsky-Rosen, the wormholes of general relativity and the entangled pairs of quantum theory might be two descriptions of the same underlying reality. If so, what we call space could be nothing more than a grand tapestry woven from countless threads of entanglement. Others urge caution. It is tempting, they warn, to drift into metaphysical reverie, to imagine cosmic consciousness or hidden channels of information. Yet physics, at its heart, demands empirical discipline. Entanglement is extraordinary precisely because it is measurable, calculable, and predictably strange. To leap from this to claims of universal mind or mystical unity risks leaving the solid ground of evidence for the shifting sands of speculation. The awe it inspires need not be diluted by such leaps. Indeed, the raw fact that reality behaves this way is wonder enough. And yet the mystery lingers. For every precise equation describing the correlations, for every experiment that closes another loophole, a deeper question remains. What exactly is doing the connecting? We can describe the mathematics of entanglement with flawless accuracy, yet the intuitive picture, the mental model of how two distant particles know each other's fate, slips through our grasp. Perhaps the question itself betrays our classical bias. Perhaps there is no mechanism, only a reality that does not divide cleanly into separate parts. In the end, quantum entanglement is both a triumph of human reason and a humbling reminder of its limits. It shows us that the universe is not a mere collection of billiard balls bouncing through empty space, but a deeper, more subtle order where separation is an illusion and connection is fundamental. The secret wires of the cosmos are not wires at all, but patterns of relation that defy the ordinary boundaries of distance and time. We can measure them, predict them, even harness them for emerging technologies like quantum computing and cryptography. But to fully comprehend their essence, we truly understand why the universe allows such instantaneous intimacy remains beyond us. Perhaps that is precisely the gift of entanglement. It confronts us with evidence that is undeniable and a mystery that is inexhaustible. In its quiet insistence that reality is more interconnected than our most daring classical dreams, it invites us to keep looking deeper, to keep asking whether the true fabric of the cosmos is woven not from matter and energy alone, but from the very act of relation itself. Retrocausality, when effects precede causes, imagine standing at the edge of time itself, where the familiar arrow of cause and effect, our most trusted compass, suddenly spins like a disoriented magnet. We are conditioned to believe that what happens must flow from what has already happened. A glass falls because a hand slipped, a star explodes because its core collapsed. Yet, in the strange territory of quantum mechanics, this seemingly unshakable sequence begins to tremble. What if the future could whisper to the past? What if tomorrow's choices could ripple backward, shaping events that by every measure of common sense have already occurred? This provocative idea bears a name both thrilling and unsettling: retrocausality. Far from mere science fiction, it arises from some of the most profound puzzles in physics puzzles that force us to question whether cause and effect are as inviolable as we once believed. To appreciate its daring implications, we must step into the haunting theater of quantum experiments, where reality itself seems to await our questions before deciding what it has always been. Consider the classic double-slit experiment. A single particle, like an electron or a photon, is fired toward a barrier with two openings, and behind the barrier lies a detection screen. When no one looks to see which slit the particle travels through, an interference pattern like ripples overlapping on a pond emerges, revealing the particle's wave-like nature. But if we measure which slit it passes, the interference vanishes. The particle behaves like a tiny bullet. The act of measurement seems to determine not just what we know, but what actually is. Now add a twist devised by the visionary physicist John Wheeler: the delayed choice experiment. In Wheeler's scheme, the decision to observe the particle's path is made only after it has already passed the slits. Logic suggests that the particle should have already decided how to travel before our last second intervention. Yet the outcome still aligns with the measurement we choose later. It is as if our future choice reaches backward, rewriting the particle's history. This is not sleight of hand. Repeated experiments confirm it. The pattern on the screen reflects the measurement setup chosen after the particle has traversed the slits. Such results tempt us toward a daring conclusion that the universe does not fully commit to a past until the present demands it. Cause seems to trail effect, like a shadow arriving too late. Mainstream physicists tread carefully here. They often argue that retrocausality need not mean literal messages from the future. Instead, they speak of quantum states as a web of correlations on local connections that defy classical timing. The mathematics of quantum theory does not explicitly require time to run backward. It merely refuses to honor our intuitive order of events. From this cautious view, delayed choice experiments do not prove that the future acts on the past, only that our classical notion of a fixed past is too naive. And yet, there are those who lean into vertigo. Among them, advocates of the two-state vector formalism, a radical interpretation that treats the quantum world as shaped by boundary conditions both in the past and in the future. In this picture, the state of a quantum system is described not by a single evolving wave, but by two waves, one evolving forward from the past and another evolving backward from the future. Only when these two meet is reality fully defined. Measurement becomes the handshake of past and future, a conspiratorial rendezvous across time itself. This framework offers a startling symmetry. The laws of physics. It insists care not whether time flows forward or backward. If nature's equations are truly time reversal invariant, why should we grant the future less authority than the past? Retrocausality, in this light, is not an aberration, but a natural extension of quantum mechanics' deepest symmetries. Still, the proposition unsettles. If tomorrow's choices can influence yesterday's events, what becomes of free will? Could we, unknowingly, be agents in a cosmic feedback loop, our intentions rippling backward to sculpt the very conditions that shaped us? The mind rebels, grasping for the reassuring solidity of chronological order. Yet the evidence stands like a quiet riddle. Photons and electrons do not obey our psychological arrow of time. Between the sober caution of mainstream science and the speculative daring of fringe thinkers, a profound tension emerges. Is retrocausality merely a linguistic trick, a rephrasing of quantum non-locality? Or is it a window into a universe where time's fabric is more like a Mobius strip than a one-way street? The observer's paradox, consciousness as a time bridge. Imagine standing at the edge of a cliff at night, the ocean below a sheet of black glass. The moonlight touches the surface, but it is only when you gaze upon it that a sudden shimmer erupts, an instantaneous glint that wasn't there until your eyes found it. In the quantum world, this metaphor is not mere poetry. It is an unsettling hint that reality itself may awaken only when observed. For decades, quantum mechanics has carried a whisper of this mystery. At the heart of it lies the measurement problem, the puzzle of how a particle's many possible states, spread like an invisible cloud of probabilities, suddenly contract into a single outcome when we look. Before the act of measurement, an electron is not here or there, but described by a wave function, a mathematical haze of all potentialities. Yet the moment an observation occurs, that haze collapses and a single, definite fact appears. It is as if nature waits for a witness before deciding which story to tell. Some physicists recoil from this implication. The Copenhagen interpretation, formulated in the early 20th century, proposed that the observer plays a central role in determining reality. But even Niels Bohr, one of its architects, warned against slipping into mysticism. He insisted that observation meant an interaction with a measuring device, an apparatus, not a conscious mind. Still, the troubling image remained. Consciousness seemed to lurk in the mathematics like an uninvited guest who nonetheless holds the keys to the house. This is the heart of the observer's paradox. Is the human mind merely recording an objective universe, or is it a participant in bringing that universe into being? John Archibald Wheeler, one of the 20th century's most daring theoretical physicists, leaned toward the latter. He proposed a participatory universe, a cosmos in which observers are not passive spectators, but active contributors to reality's unfolding. His provocative thought experiments, such as the delayed choice experiment, suggest that choices made in the present can influence the behavior of particles in the past, as if time itself is pliable under the gaze of awareness. Consider the famous double-slit experiment. Fire a stream of electrons through two narrow openings and you get an interference pattern of waves overlapping like ripples in a pond unless you observe which slit each electron passes through. The moment you watch, the pattern changes to resemble individual particles. It is as if the electrons know when they are being observed and adjust their behavior accordingly. Wheeler's delayed choice variant takes the puzzle further. The decision to measure which path the particle takes can be made after the particle has already traversed the slits. Yet the outcome behaves as though the later choice reached back in time to dictate the earlier event. Such experiments invite an almost mythic reading. Could human awareness be a bridge between what we call now and what we call then? If our conscious observation can influence events that have already occurred, the neat line we draw between past and present begins to blur. In Wheeler's vision, the universe is not a fixed stage, but a grand self-exciting circuit in which observers and the observed co-create reality across the span of time. It from bit, he famously declared, physical reality. The it arises from the yes or no questions asked by observers of the bits of information. Yet not everyone is willing to grant consciousness such cosmic authority. Materialist thinkers argue that the collapse of the wave function need not involve awareness at all. Decoherence theory explains how interactions with the environment stray photons. Air molecules, vibrations can effectively measure a quantum system, forcing it into a definite state long before any human eyes intervene. From this view, the universe needs no witness. It simply follows the mathematics of entanglement and entropy. To suggest that human minds shape the past is, to these critics, a romantic leap beyond evidence. Parallel worlds and the many timelines. Hypothesis: imagine standing at a crossroads where every choice you make, every heartbeat, every hesitation splinters reality into countless threads. In one, you turn left and meet the stranger who alters your destiny. In another, you turn right and never know their name. The many worlds interpretation of quantum mechanics dares to say that these possibilities are not mere fictions of imagination, but living, breathing realities. Every quantum event, no matter how small, becomes the seed of a new universe. Each branch carries forward its own history, its own version of you, unfolding in directions you will never witness. The idea was first set down by physicist Hugh Everett III in 1957, a quiet revolution cloaked in mathematical logic. He proposed that the strange probabilistic nature of quantum mechanics is not a flaw in our understanding, nor a veil hiding a single predetermined outcome. Instead, every outcome that could happen does happen, each in its own distinct world. The electron passes through both slits. The cat is both alive and dead. We simply inhabit one strand of this infinite cosmic braid. For centuries, science held fast to the vision of a single, deterministic universe, a grand clockwork, where if you knew every particle's position and momentum, you could calculate the future with unerring precision. Newton's laws whispered of a cosmos ruled by certainty, but the quantum realm shattered that narrative. In the dance of subatomic particles, probabilities replaced inevitabilities. The Copenhagen interpretation suggested that reality crystallizes only when observed. Everett's radical proposal swept away the need for such a collapse. Nothing collapses because everything happens. Observation does not decide the outcome. It merely reveals the branch you happen to occupy. This view is both liberating and unnerving. If every choice spawns a parallel world, then infinite versions of you roam the multiverse, some thriving, some floundering, some unrecognizably transformed. In one universe, you became a musician. In another, you never learned to read. In countless others, you never existed at all. These are not distant galaxies you could one day visit. They are adjacent realities separated by the thinnest of quantum membranes, forever inaccessible yet hauntingly near. And yet, the mind cannot help but wonder, if these worlds truly exist, are they forever sealed off? Or could subtle quantum pathways entanglements that defy classical limits allow echoes to pass between them? Some speculative physicists have toyed with the idea that information might leak through the cracks, that a decision in one branch might ripple into the awareness of its neighbors. Perhaps a sudden intuition, a dream that feels more like a memory, is the faint whisper of another self nudging you. It is a thought more poetic than proven, but it captures the eerie allure of quantum theory's unfinished business. This possibility redefines the very notion of destiny. The deterministic universe offers comfort in its predictability. The future, though hidden, is fixed. The multiverse, by contrast, is a storm of branching timelines, where every outcome is realized and no single thread can claim supremacy. Your choices matter not because they carve the future from stone, but because they determine which version of you will experience which path. Free will is not the power to change the future for all worlds, but the act of selecting the perspective from which you will remember it. Still, the implications are dizzying. If infinite versions of yourself exist, which one is the real you? Identity, once anchored in a single narrative, dissolves into a fractal of possibilities. We become not solitary beings, but an ever-expanding constellation of selves, each living out a different permutation of our potential. Existence itself becomes an orchestra of alternate melodies, each played in perfect simultaneity, beyond our hearing, yet part of a larger cosmic score. Some philosophers argue that this vision breeds a quiet existential unease. In a universe of infinite copies, what does it mean to succeed or fail? If in one branch you conquer your fears and in another you fall to them, is either victory or defeat truly yours? The multiverse undermines the solace of uniqueness, yet it also magnifies the mystery of being. You are at once indispensable and infinitely replicated, a paradox that both humbles and exalts. Science approaches these questions with caution. Evidence for many worlds is indirect, woven into the very mathematics of quantum theory rather than displayed in experimental proof. Critics contend it multiplies entities needlessly. Why invoke infinite universes when a single one suffices? But proponents counter that Everett's framework is not extravagant, it is economical. It requires no additional rules, no arbitrary collapse. Reality, in this view, is not a singular story, but an endless library where every quantum chapter is written. The debate cuts to the heart of what we believe reality to be. A single, shared narrative or a shimmering mosaic of overlapping truths. The many worlds hypothesis invites us to imagine a cosmos where every what if is not an idle speculation, but a living fact. It asks us to see ourselves not as solitary travelers, but as members of a vast, unseen multitude, each choosing a doorway, each moment a new universe blooming into being. If we dare to follow this logic, our sense of existence expands beyond comprehension. The night sky no longer holds a single universe of stars. It holds countless layers of reality, stacked and unfolding like an endless cosmic origami. Somewhere, another version of you looks up and wonders the same thing, feeling the same shiver of recognition. The question that lingers is not whether these worlds exist, but what it means for us to know or even suspect that they might. Time loops and the cosmic feedback imagine standing on a quiet ridge at night where the sky spills an ocean of stars. Each point of light is a frozen whisper from millions of years ago. We take it for granted that the universe speaks in one direction, only that cause precedes effect, that time is an arrow which never bends. Yet hidden deep in the mathematics of general relativity lies a far stranger possibility. Time might curve back on itself, forming loops where the end meets the beginning. Einstein's equations, so often celebrated for their elegant simplicity, contain within them the seeds of their own subversion. In 1949, Kurt Gödel, already renowned for shaking the foundations of logic, unveiled a rotating universe solution to these equations. Gödel's cosmos did not merely spin, it twisted the fabric of space-time into closed, time-like curves, pathways through which a traveler could, in principle, return to their own past. The notion defied the everyday rhythm of sunrise and sunset, challenging the bedrock of causality itself. A generation later, physicist Frank Tipler pushed the concept further. He envisioned a hypothetical, infinitely long cylinder rotating at near light speed. Around such a cosmic dynamo, space-time would spiral like a corkscrew, creating corridors of closed time. It was a thought experiment as audacious as it was precise, a cosmic machine that would make time its plaything. Tipler's calculations revealed that within the embrace of this endless cylinder, the traveler could trace a curve through space-time that looped back to an earlier moment, effectively writing their own history. These solutions are not poetic metaphors, they are rigorous consequences of Einstein's own equations. And therein lies the tension. The mathematics gleams with an almost Platonic beauty, yet it opens a door to paradoxes so profound they unsettle the very idea of reality. You can visit yesterday. What becomes of free will? Does the decision you make now ripple backward to shape the conditions that allowed you to make it? The simple phrase cause and effect begins to dissolve, as if the very language of time cannot keep pace with its own curvature. Philosophers have long wrestled with the nature of choice, but a universe with genuine time loops would elevate their debate to cosmic scale. Consider the so-called grandfather paradox. If you travel back and prevent your ancestors from meeting, do you erase yourself from existence? Or does the universe find some self-consistent way to mend the contradiction? The mathematician's answer is often to invoke self-consistency principles, as if reality were a seamless narrative that never allows an edit to break the plot. But for the human heart, the question cuts deeper. If every action is already embedded in a closed loop, are we actors or merely characters playing lines that have already been written? Now imagine this not as a solitary traveler's whim, but as a property of the cosmos itself. Picture colossal galactic filaments, vast threads of matter that span hundreds of millions of light years, acting as giant resonators. In this speculative vision, gravity's deep hum could ripple both backward and forward along the fabric of space-time, like a cathedral echoing with overlapping chants. The universe might carry information from tomorrow into yesterday, a cosmic feedback that binds past and future in a single, resonant chorus. Such imagery seduces the imagination. The universe, instead of a linear tale, becomes a vast symphony in which every note is heard, both before and after it is struck. The birth of a star might whisper its song into epochs long gone. The collapse of a galaxy might send tremors into ages yet unborn. To contemplate this is to feel the ground of ordinary time tilt beneath one's feet, to sense that the present moment is less a fleeting instant than a standing wave in a timeless sea. Yet the very audacity of these ideas summons their own skeptics. Mainstream physicists often treat Gödel's rotating universe and Tipler's infinite cylinder as mathematical curiosities, clever constructions that reveal the pliancy of Einstein's equations, but not the behavior of the real cosmos. Our universe, after all, is not observed to be rotating in the way Gödel required. Tipler's cylinder would need to be infinitely long, an engineering project beyond even the reach of speculative alien civilizations. For many researchers, these requirements push time loops from the realm of physics into that of philosophical fiction. Moreover, the known laws of quantum theory and thermodynamics raise sharp barriers. Quantum field theory suggests that even small perturbations might destabilize such closed, time-like curves, causing infinite energy densities that would tear the structure apart before any traveler could step inside. The second law of thermodynamics, with its insistence on an ever-increasing entropy, resists the notion of a perfectly repeating loop. To many scientists, these are not mere technical obstacles, but signs that nature herself polices the boundaries of time. Still, the paradox refuses to vanish. The mathematics remains like a quiet riddle etched into the foundations of space-time. For those drawn to the edges of knowledge, the possibility of cosmic feedback remains a siren call. What if the universe does, in some hidden dimension, listen to itself across time? Experiments at the edge of time. It slips past our fingertips, a silent river no eye can see, no hand can hold. Yet in laboratories across the world, scientists dare to press against its current, constructing experiments so precise they almost sound like fiction. Their aim is audacious, to probe whether time itself is as unyielding as we assume, or whether, under the microscope of quantum and cosmic inquiry, it begins to bend. Consider the quantum eraser. At first glance, it resembles a conjurer's trick, but its foundation is as solid as any other cornerstone of quantum mechanics. In a classic double-slit experiment, particles of light behave as though they know when we are watching, observe them, and they march like soldiers through one slit or the other. Turn away, and they smear into a wave of possibilities, producing interference fringes. The quantum eraser adds a startling twist. By erasing the very information that reveals which path the photon took, sometimes even after the photon has already passed, the slit's interference returns. It is as if the decision to behave like a particle or a wave is influenced not at the moment of flight, but retroactively, as if the photon can sense our later choice. Physicists are careful with their words. They will insist no actual message travels backward. The mathematics of quantum theory remains intact. Yet the experiment leaves an aftertaste of temporal mischief. How can an action performed in the present appear to sculpt a pattern that was seemingly fixed in the past? The result is not a crude time machine, but it blurs the very notion of a single, universal sequence of events. Even in their caution, researchers feel the pulse of something profound, time, that most ordinary of dimensions may not be the one-way street we take for granted. If the quantum eraser whispers of microscopic ambiguity, gravitational wave observatories shout of cosmic drama. LIGO and its global siblings listen for ripples in the fabric of space-time itself, stirred by the cataclysmic embrace of black holes. Each chirp arriving at their detectors carries the story of collisions billions of years old. To hear those waves is to eavesdrop on the universe's most violent dances, but it is also to confront the relativity of time with experimental force. When two black holes spiral together, they twist space-time so fiercely that time dilates. For observers near the merging pair, seconds stretch. For us, far away, the event unspools in its own tempo. The gravitational waves reach our detectors after an odyssey across eons, revealing that time is not a universal metronome, but a malleable field that bends with mass and motion. Here, Einstein's equations cease to be abstract. The laboratory is the cosmos itself, and the data stream proves that simultaneously our everyday sense that moments are shared has no absolute meaning. From the vastness of colliding black holes, we descend to a quieter theatre, the realm of precision atomic clocks. These devices, cooled to near absolute zero, trap atoms and measure the oscillations of their electrons with astonishing fidelity. Today's optical lattice clocks can keep time so precisely they would lose less than a second over the lifetime of the universe. But more striking than their accuracy is what they reveal. Place one clock a few centimeters higher than another, and the tiny difference in gravitational potential makes it tick ever so slightly faster. Such measurements confirm general relativity's prediction that gravity and velocity warp time, yet they also provoke subtler questions. If even a change in floor height alters the tempo of time, what becomes of our naive belief in a single, synchronized now? Our sense of simultaneity crumbles, replaced by a patchwork of local times stitched together by relativity's mathematics. The result is a quiet but revolutionary realization. Time is not a backdrop against which the universe acts. It is an active participant, responsive to matter and motion. These experiments, quantum, cosmic, and terrestrial, form a spectrum of inquiry. On one end lies the disciplined certainty of measurement. Lasers, tuned to unimaginable exactness, detectors isolated from the Earth's tremors, equations tested to the last decimal. On the other end lingers a dream as old as myth, to send a message backward, to tip the arrow of time the other way. The rigor of the laboratory and the allure of temporal rebellion meet in a tension that defines our age of discovery. Scientists stand between these poles, guarding against fantasy even as their results invite it. Ancient mystics and modern physicists, from the temples of ancient India to the high-energy laboratories of contemporary physics, humanity has long stood before the riddle of time like a traveler, staring into a river that flows both toward and away from the source. The language of mystics and the equations of physicists might seem worlds apart, yet both are driven by the same yearning to glimpse what lies beyond the veil of ordinary hours and minutes. The old sages spoke in parables, the new scientists in symbols and measurements, but the question remains eerily similar. Does time move as we think it does? Or is it a far more fluid and elusive dimension than our senses suggest? In the quiet halls of Buddhist monasteries, long before particle accelerators smashed atoms in search of hidden truths, the notion of timelessness was not merely a philosophical curiosity. To the meditator seated in stillness, time dissolves like a mirage. Past and future lose their edges, and the present stretches into something boundless. Buddhist texts speak of the unborn nature of reality, a state beyond arising and passing, where time is not a river but a reflection of an illusion cast upon the mind. This is no casual metaphor. It is an experiential claim. When one enters deep states of awareness, the ticking clock fades, and consciousness itself becomes a horizon without beginning or end. Half a continent away and centuries earlier, Hindu cosmologies traced a grander cycle, the yugas, immense epochs that rise and fall like the breath of the universe. Here, time is not an arrow shot once and for all toward an eventual oblivion. Instead, it spirals, endlessly repeating its cosmic seasons. Ages of creation and dissolution follow each other in eternal recurrence, suggesting that the universe is neither a singular event nor a final destination, but a breathing organism of infinite rebirth. Within this vision, the human lifetime is a mere blink, and the so-called beginning of time is simply one of countless dawns. Across oceans, indigenous traditions also whisper of temporal mysteries. From the Hopi prophecies of cyclical worlds to the Mayan long-count calendar, time emerges not as a straight line but as a living pattern, weaving past and future into a sacred dance. These cultures describe prophecy not as prediction in the narrow sense but as participation in an eternal rhythm. For them, time is a ceremony, a spiral of renewal in which ancestors and descendants coexist in the shared heartbeat of creation. At first glance, modern science would appear to stand at the opposite pole of such mythic imaginings. Physics, after all, prides itself on empirical caution, on measurements that can be tested and repeated. Yet when the equations of relativity and quantum mechanics are pushed to their limits, the universe begins to sound strangely familiar to those ancient voices. Einstein's theory of relativity reveals that time is not a universal constant but a pliant fabric, stretching and contracting depending on speed and gravity. For a particle moving at near light speed, the difference between seconds and millennia collapses. The traveler may barely age while centuries pass elsewhere. Quantum theory deepens the mystery. At the smallest scales of existence, the sharp division between past and future blurs. Subatomic events can seem to influence one another across time as well as space, as though cause and effect were not chained in a simple forward march. Some interpretations even flirt with the idea that all moments past, present, and future coexist in a vast block of space-time, a cosmic manuscript already written. If that sounds suspiciously like the timelessness of Buddhist meditation or the eternal cycles of Hindu thought, it is because our most sophisticated science, when followed to its logical conclusion, begins to rhyme with the most ancient intuitions. Yet the physicists, for all their daring, are careful not to mistake metaphor for proof. Where the mystics speak of direct experience and spiritual insight, science demands evidence that can be tested and falsified. The Buddhist monk may say time vanishes in meditation, but the physicist insists on experiments to show how time behaves under gravity's influence. This tension between inner revelation and external verification forms a productive contrast. It reminds us that mystery alone is not enough. Wonder must be tempered by rigor if we are to separate what is possible from what is merely poetic. Still, the echoes are undeniable. When a cosmologist describes the early universe as a quantum foam where time itself had no definite direction, we hear an ancient chord struck anew. When an indigenous elder speaks of ancestors present in the circle of the living, we catch a resonance with the physicist's vision of a space-time where all events eternally coexist. Even the cautious skeptic can feel the pull of this convergence, a reminder that human beings across epochs have sensed that time is not what it appears. Why do these parallels matter? Perhaps because they show that our hunger to understand time is not confined to laboratories or temples, it is a universal impulse. Ancient mystics framed their insights in myth and ritual, modern scientists in mathematics and observation. But both paths lead us to the threshold of the same enigma, that the reality we inhabit may be less like a clock and more like an infinite ocean, where beginnings and endings dissolve. In confronting this mystery, we are united across centuries and cultures. The mystics' chant and the physicists' equation, though born of different traditions, invite us to reconsider the most intimate dimension of existence. Time, which governs every heartbeat and every star's death, may be far less stable than we imagine. And as these worlds of ancient wisdom and modern physics whisper to each other across the gulf of history, they reveal a shared intuition that to truly grasp the nature of time is to stand on the edge of something larger than comprehension, where science and spirit meet in awe. Personal encounters with tomorrow in every age. Across continents and cultures, there lingers a quiet rumor that tomorrow sometimes leaks into today. It arrives not as a thunderclap of prophecy, but as a whisper, an unshakable feeling, a flash of recognition, a dream that later unfolds in waking life with unsettling precision. From the seers of antiquity to the most rational minds of the modern world, people continue to report experiences that seem to bend the arrow of time, leaving even hardened skeptics momentarily breathless. Consider the countless stories of premonition. A mother awakens in the night, inexplicably compelled to call her son, only to discover he has just been in an accident. A traveler changes his route at the last minute and avoids a disastrous crash. A scientist dreams of an equation he has never consciously conceived and wakes to find it correct. Such moments, often mundane and profoundly personal, carry the fragrance of something impossible. They refuse to be dismissed as mere coincidence because they pierce the fabric of our ordinary understanding of cause and effect. Déjà vu carries a different flavor of temporal strangeness. That sudden, eerie sensation that the present has already been lived, like stepping into a memory you never formed, has haunted philosophers since the term was first coined. You walk into a room you have never seen, yet every detail feels achingly familiar. The angle of sunlight, the cadence of a stranger's voice, even the smell of the air. For a few seconds, you hover between timelines, as if some part of you has already rehearsed this scene in an unseen theater. Science offers partial explanations of neurological misfires, a momentary lag between the brain's memory systems, but the feeling itself is stubbornly resistant to tidy categorization. It leaves behind a residue, a suggestion that perhaps memory is not only about the past. Intuition, too, often plays the role of messenger from a future we cannot yet inhabit. Inventors speak of flashes of insight that arrive whole, unbidden, as if ideas were already waiting in the wings. Ordinary people describe a gut certainty to act or to hold back without any conscious reasoning, only to discover later that this instinct preserved them from danger or guided them toward an unforeseen opportunity. These private experiences blur the boundary between foresight and chance, inviting a question as old as myth. Is there a dimension of mind that peers beyond the present moment? Psychology offers a sober lens. Cognitive scientists remind us that the human mind is a master of pattern recognition, a storyteller weaving meaning from randomness. We remember the hits and forget the misses. A single striking coincidence can eclipse 1,000 uneventful days. Memory, far from being a flawless recording device, is malleable and selective. The dream that seems predictive may be a reconstruction, shaped after the fact to fit the outcome. Déjà vu might arise from a glitch in the temporal sequencing of the hippocampus, where familiarity registers before conscious awareness catches up. Intuition, for all its mystery, can often be traced to subconscious processing, the quiet accumulation of sensory cues and hidden knowledge surfacing as a sudden certainty. These explanations are persuasive and, for many, sufficient. They protect the logical architecture of reality, ensuring that cause still precedes effect, that time moves in a single direction. And yet the stories persist too numerous, too striking to dismiss without at least a shiver of doubt. There are moments when even the most careful scientist wonders whether something deeper is at play, something that hints at a reality far stranger than our models allow. Some researchers in the fringes of physics and consciousness studies speculate about quantum information as a possible bridge across time. In the quantum realm, particles can become entangled, their states linked instantly across distance, and some daring thinkers suggest perhaps even across time. Could our minds, in ways not yet understood, tap into a field of information where past and future intermingle? Might déjà vu be a brief entanglement between present perception and a future already encoded in the quantum fabric? Others turn to Carl Jung's notion of the collective unconscious, a shared psychic reservoir where symbols, archetypes, and perhaps even fragments of future events circulate beyond the reach of individual awareness. From this vantage, a premonitory dream might be less about a private prophecy and more about the psyche brushing against a pattern emerging in the collective mind. Intuition could be the faint signal of this deeper network, a whisper from the shared depths that guides individuals toward events not yet visible on the surface of time. Skeptics caution that these ideas, while seductive, remain speculative. Quantum mechanics is often misappropriated to justify metaphysical claims it cannot support. Entanglement across time remains an untested hypothesis at best. Jung's collective unconscious, though rich in metaphor, is not a scientific model but a psychological framework. The allure of such theories lies partly in their mystery. They give form to the intuition that reality might be more interconnected, more fluid than the empirical world suggests. Yet the power of these personal encounters with tomorrow does not rest solely on their explanation. Whether they are products of coincidence neurology or a deeper order of reality, they open a crack in the familiar wall of time. They awaken a vertigo of possibility that the future is not a sealed corridor, but a landscape already casting shadows backward. They invite us to contemplate our own participation in a cosmos where information might flow in ways we have barely begun to imagine. Perhaps the true significance of premonitions, déjà vu, and sudden intuitions lies in their capacity to challenge certainty. They remind us that our understanding of time is provisional, a story we tell to make sense of experience. Whether these experiences are mere quirks of memory or glimpses of a larger pattern, they stir the same quiet awe in the sense that we inhabit a universe still full of secrets, where tomorrow sometimes leans close enough to whisper its name. The ethics of knowing the future. Imagine a world where tomorrow is no longer a mystery. Not the vague intuitions we carry when we say we have a feeling, but a precise unveiling of dates, events, decisions already mapped and waiting. At first blush, such knowledge sounds like a gift, a shimmering thread of certainty in the chaotic weave of existence. Yet beneath the glitter lies a question that has haunted philosophers for centuries. If the future can be known, can it also be changed? Free will has always been the human anchor against the vast currents of the cosmos. We cherish the belief that each choice, however small, bends the arc of our story. But if someone or something can peer ahead with flawless clarity, the illusion begins to crack. Suppose a scientist develops a method to see the outcome of every major decision. Does the act of knowing that outcome predetermine our path, or can we still defy the script? The paradox cuts deep. To know is to influence, yet to influence is to admit that the future was never fixed. Philosophers of determinism argue that the universe operates like an intricate clockwork, each effect the inevitable child of prior causes. In their eyes, knowledge of the future would merely expose what was already set. Freedom, they insist, is a comforting mirage. Our choices are the ripples of a river whose course was drawn at the dawn of time. Yet the champions of freedom will push back. They claim that even if tomorrow can be forecast, consciousness grants us a unique power, the ability to interrupt, to swerve, to rewrite the script precisely because we are aware of it. This tension between foreknowledge and agency carries profound moral weight. If every decision is inevitable, what becomes of responsibility? Can we hold someone accountable for actions that the cosmos dictated long before they were born? A future visible in advance would not only challenge courts and laws, it would force each of us to confront our own sense of guilt and virtue. Punishment, praise, even forgiveness, these would all shimmer with a strange ambiguity if we knew the accused never had a choice. Utopian visions paint foreknowledge as a balm for human suffering. Imagine averting disasters before they strike, curing diseases before symptoms appear, steering societies away from economic collapse or war. In this dream, foresight becomes the ultimate form of compassion, a tool to spare humanity its deepest pains. Governments could plan with unprecedented wisdom. Individuals could avoid heartbreak and loss. The future, once feared, would become a garden carefully tended in advance. Yet dystopian shadows stretch just as far. Knowledge of tomorrow is power that tempts manipulation. If a handful of elites could foresee markets, elections, or personal choices, the imbalance would be staggering. Democracy would wither under the weight of those who always knew the outcome. Free societies thrive on uncertainty, on the belief that tomorrow can be shaped by the many, not dictated by the few. With prophetic data in the wrong hands, freedom could become a relic, replaced by the cold precision of control. History already offers cautionary whispers. From ancient oracles to modern algorithms, those who claim to predict the future often wield influence far beyond their accuracy. The mere belief in prediction alters behavior, markets surge or crash, leaders hesitate or strike, lovers cling or let go. Whether the forecast is true or false, the psychological impact is real. We live differently when we believe the future is already speaking. Consider the quiet despair of a person told their destiny cannot change. Hope becomes a fragile echo, ambition an empty gesture. Yet for others, the same knowledge might ignite rebellion and a fierce determination to prove fate wrong. Human psychology dances between resignation and defiance, and foreknowledge would magnify that dance to cosmic proportions. Some would surrender to the script, others would burn it. The ethics of knowing the future therefore reach beyond philosophy into the intimate corridors of the mind. To reveal what is to come is to reshape the present. Each revelation ripples backward, influencing decisions that were once spontaneous. Foreknowledge is not passive observation. It is participation, a catalyst that transforms both seer and seen. And perhaps this is the deepest mystery. The act of knowing the future might change the future itself. The prediction becomes part of the equation, a self-altering loop where certainty dissolves the moment it is touched. In this subtle paradox lies a strange hope. Even if tomorrow could be glimpsed, perhaps it can never be fully captured. The universe may always guard a corner of surprise, ensuring that freedom, however fragile, survives the temptation to know. Echoes of Infinity, closing the temporal loop, began with a question that lingers like a faint vibration across the corridors of thought. Are the whispers we hear in quantum reality the echoes of our own destiny? As we arrive at the edge of our journey, the question has not faded. It has deepened. It waits, patient and enigmatic, as if the universe itself were listening to our wondering. Throughout the long arc of human inquiry, time has been the most elusive companion. We have charted the stars, built equations to measure the motion of planets and particles, and yet the flow of time remains a riddle that no clock can capture. Physics tells us that the past, present, and future may coexist in a single, four-dimensional tapestry, an eternal block where every moment simply is. Yet, we live inside the sensation of passage, bound to a moving present like travelers crossing a bridge we can never see in full. This tension between what the mathematics whisper and what our hearts feel carries the pulse of the mystery. Quantum theory complicates the story further. At the smallest scales of existence, time refuses to behave as we expect. Particles appear to anticipate outcomes. Entangled partners exchange information as though distance and sequence mean nothing, and the arrow of time bends under the weight of probability. Are these phenomena merely quirks of measurement, or are they signposts hinting that our classical understanding of past and future is only a thin slice of something vast? The great physicists who gave us these revelations, Einstein, Bohr, Wheeler, were themselves philosophers of the infinite. Einstein spoke of time as a persistent illusion, a human perception imposed upon a cosmic order that does not share our sense of before and after. Bohr reminded us that the act of observing shapes the reality we observe, a dance where mind and matter cannot be fully separated. Wheeler asked whether the universe might be a grand participatory experiment, where reality crystallizes only when consciousness looks upon it. Each of these visions invites us to hold science not as a collection of answers, but as a living invitation to wonder. And wonder, at its deepest, is an act of humility. For every theory that sharpens our grasp of time structure, another discovery widens the horizon of mystery. The early universe hums with primordial vibrations we barely decipher. Black holes fold time into knots where even light cannot escape. Quantum gravity, the long-sought bridge between the infinitely large and the unimaginably small, remains a dream sketched in incomplete equations. The closer we peer, the more the infinite recedes like a mirage at the horizon. Yet there is something profoundly human in this chase. We are finite beings daring to contemplate the eternal. Our lifespans are brief sparks against the cosmic dark, and still we imagine the beginning and the end of all things. We give names to epochs older than our planet. We measure the afterglow of creation, and we dream of futures billions of years ahead. This audacity is not arrogance. It is the signature of consciousness itself, the strange capacity of the universe to reflect upon its own becoming. Perhaps time is not a river carrying us forward, but a dimension we inhabit, every instant coexisting, every possibility already woven into the cosmic fabric. If so, our sense of moving through moments might be like tracing a finger across a painting. We experience sequence, but the masterpiece exists all at once. In this view, destiny is not a fixed endpoint, but the unfolding recognition of a pattern that has always been there. And yet, speculation must walk hand in hand with evidence. Science demands rigor, measurements, predictions that can be tested. The humility of our knowledge lies in knowing how much we cannot yet prove. Quantum mechanics gives us probabilities, not certainties. Cosmology offers models, not final answers. The frontier of understanding is not a fortress, but an open horizon where every discovery raises new questions. This is not a failure of science, it is its truest power. Beyond equations and experiments, there is an even deeper mystery, that the universe is capable of being known at all. Why should the human mind, an emergent pattern of neurons in a small corner of a spiral galaxy, be able to decipher the laws of space-time and the dance of subatomic particles? Perhaps this capacity is not accidental. Perhaps consciousness is not merely a byproduct of matter, but an essential feature of reality, as fundamental as space and time. Consider the possibility that when we explore time, we are not merely observing something external, but encountering a mirror. The quantum echoes we detect in experiments may be reflections of our own nature, the dialogue between mind and cosmos playing out across the dimensions we seek to measure. The observer and the observed are intertwined, their destinies braided in ways we scarcely comprehend. Such thoughts do not diminish the grandeur of science, they magnify it. For science is not only a method of calculation, but a voyage of meaning. It reminds us that the more we learn, the more the unknown expands. Our equations may capture the curvature of space-time, but they cannot exhaust the infinite. Our instruments may trace the birth of galaxies, but they cannot reveal the ultimate origin of being. In this tension between knowledge and mystery, awe is born. Awe is more than astonishment. It is the recognition of something larger than ourselves, something that humbles and elevates in the same breath. It is the feeling of standing beneath a sky ablaze with stars, sensing that each point of light carries the memory of billions of years. It is the quiet realization that the atoms in our bodies were forged in stellar furnaces long before Earth was born. It is the unshakable intuition that our consciousness is both fleeting and timeless, a brief window through which the universe contemplates itself. Perhaps this is the true echo of infinity. Not a sound carried across space, but a resonance within us. We are the cosmos reflecting on its own story, a momentary expression of something endless. Time does not merely pass through us, we are time thinking, feeling, questioning. Our search for the nature of past and future is the universe awakening to its own mystery. And so we return to the question that opened this journey. Are we hearing quantum echoes of our own destiny? We cannot yet answer. Perhaps destiny is not something that lies ahead, but something that unfolds in every instant, in every act of curiosity, in every breath of wonder. Perhaps the echo is not a prediction, but an invitation to keep listening, to keep imagining, to keep reaching beyond the limits of what we know. The loop is not a cage, it is a circle of discovery, unending, luminous. The more we seek, the more the horizon expands. Time remains an open frontier, a vast and silent expanse where science and philosophy meet in a single, breathless question. And in that question we find not certainty, but something greater, the eternal call of mystery, beckoning us ever onward.